In this video, I'm going to show an example of analyzing a CSV file of acceleration data. So you go to Google Colab, which is a free way to run Python code. It's pretty cool, and it's all hosted in the cloud. You can run this locally as well. But to start, you need to import your libraries. You just hit run here. These are libraries of various packages and functions we'll use throughout this analysis. These are all built into Colab. If you want to use a library that doesn't exist as a built-in, you can do pip, !pip space install, and then the library name. We're using things already built in. So once we've imported some of these main libraries, we can also go to import the file itself, which you hit that choose files and then select the file you want to use. And it will take a moment as it imports. I will say that I'm assuming the CSV has column names, and the first column I'm assuming is time in parentheses S for time in seconds. So make sure that CSV you're going to use has column names, and the first column being time in seconds. So now it's imported, and I can run this cell, which will just convert it into a data frame. And you see my first column is time in seconds, and then my second column is acceleration G. You can do any number of columns, but at least make sure the first one is time in seconds. And here I then define my time in seconds as the index, which then allows me to filter into that file pretty easily. So once I have it imported as a data frame, I can do something very simple as df.plot, and that generates this plot. I can also, because I had indexed my time, I can select a range very easily by just doing these brackets. And so I'm going to plot just from time 22 to 24 seconds. Now these plots are good. This is built into pandas. It's using a library called matplotlib, but plotly is way better. So here's a function that, given a data frame, will generate a plotly figure. So here I'm going to generate this plotly figure. I'm also going to save it to an HTML file so I can share it with somebody. And now in here, I can zoom around, and you see all this interactivity with the file. And again, this is saved as an HTML, so I don't even have to be logged into Colab or anything to access this data. You just have to look at it in a web browser. Again, you can index by just the brackets and the time range you want, and then this will just plot just in that time range from 22 to 24 seconds in this example. Now let's generate a power spectral density. We're doing that using the signal.welch function. So we'll run that cell and then actually calculate the power spectral density. The inputs are the data frame as well as the bin width in hertz that we want. And you see we have a PSD now with every 1 hertz, there's a new value. And now let's plot this. And here you go. So here's our power spectral density. Looks great. Again, it's interactive, all this good stuff. I can show you how you change these bin widths. Maybe I want to do 10 hertz instead of 1 hertz, or I want to do half a hertz to get a little more granular. That's very simple with just passing in that bin width argument. I also may want to save these again to HTML for that interactive plot, or a CSV file, which you can do just by doing psd.csv and then calling it whatever name you want. Now let's also generate a cumulative RMS from the power spectral density, which is very easy to do. And now you see here that cumulative RMS. And again, I save that to a CSV file as well as an HTML. Another thing you may want to do is generate an octave-spaced power spectral density. So here I had to declare a couple functions to do this. I won't go through that now, but you can hide that. And then once that's declared, once you've run that, you can generate this octave-spaced PSD. Here I'm passing in, the octaves I want, which is 1/3, starting at 1 hertz and going up to half the sample rate. And there you go. And I can redo this example now with some other data. Instead of importing it like I just did, I can instead read it from a known location. Here's an example file. So this is X, Y, and Z axis acceleration. Again, set the index to be the time, the first column. You can plot it here. We'll do the interactive plot. There you go. Take a moment because it's a lot of data to plot, but here it is. You can index it again by specifying the time range. Now let's calculate that power spectral density off of it. Again, it has multiple columns, so it can handle that no problem. Here's the power spectral density off that data. Again, you can change the bin width if you like, or make a cumulative RMS calculation. There'll be multiple lines for the three different columns that I had. And once you have that, you can also filter to see one column, just isolating it or clicking it in the legend, which is cool. So now you notice I've saved a couple things to CSV and HTML. So on the left-hand side, this is my table of contents of the Colab notebook. But here is also these files that I have saved, so I can download them just by clicking that. And that's a quick example about using Python to analyze acceleration data. We will have some more videos and blog content on this in the months ahead. Thanks.